This next example is spread over 2 videos because of its length, so you'll need to view this video and the next one in order to see the whole example. B lies on a rough slope and A hangs freely. We want to calculate the tension in the rope and the acceleration of the system when it is released from rest. The first thing we can deal with here is the angle of the slope. Many pupils don't like it when the slope is given in this form. However, it is quite straightforward to deal with. Just go off to the side and draw a triangle. If this is theta, we're told it's arc sine 3/5, which means the opposite must be 3, and the hypotenuse is 5. We should recognize a 3, 4, 5 triangle, giving us the adjacent as 4. Then sine theta is equal to 3/5, and cos theta is the adjacent over the hypotenuse, which is 4/5. Now consider the diagram. At A we have a 1G force acting downwards, its weight, and the tension force pulling upwards. At B, the weight of 2G acts downwards. This can be split into components perpendicular to and parallel to the surface. The perpendicular one, as always, will be the cosine of the angle, so 2G cos theta. Parallel, we will have the sine, so the force acting down this way will be 2G sine theta. We also have the tension pulling this way, and the reaction force perpendicular to the surface. We can now ignore the weight since its components have the same effect. Our object is on a rough slope, so there must be a frictional force. Friction, we know, will always oppose motion. If we decide that the object is going to accelerate down the slope, and this object will accelerate upwards, then the frictional force must act up the slope to oppose motion. Note that it doesn't matter if we got these directions wrong. We'd just get negative answers. If A comes out to be a negative, we know that it's in the opposite direction to the way we drew it on the diagram. If we now consider the perpendicular to the plane forces, we have the r and this component of the weight. Since the acceleration is parallel to the surface, these forces must be equal. So r must be equal to 2G cos theta. And of course we know the value of cos theta. So this calculates to 15.68 newtons. Now looking at object A. It's accelerating upwards, so the resultant force must be T take away 1G. And this must be equal to its mass times the acceleration. And of course its mass is 1. Looking now at B, down the slope we have the 2G sine theta, and the T and FR up the slope. So we get 2G sine theta, take away the T, take away the friction, giving us the resultant force down the slope, must be equal to its mass times the acceleration. This gives us 11.76. Take away T, take away the friction, which is mu times r, so minus 1.568, is equal to 2a. Combining these two, we get 10.192. Take away t is 2a, and we'll call this equation 2. G we take to be 9.8, and doing equation 1 plus equation 2 gives 10.192 take away 9.8. The t's will cancel, equals 3a. A is then 0.392 divided by 3, which is 0.1307 meters per second squared, working to 4 significant figures, saving the extra significant figure since we may use this in subsequent calculations. Substituting back into number 1 to find t will be 9.8 plus 0.1307, which gives us 9.9307 newtons. And we will use this result in the next part of the question, which, remember, is the next video.